mostly is Bayesian. Yeah.
Let me say, can't we compare chi-square test or goodness of fit test in frequently learning in the to find prior distribution similar to here?
So first of all, that's a good point, and in some sense, actually, again, you're going into more detail than I can expect anybody else here to understand, unless they have done statistical inference. I assume you did, but in general, for example, things like confidence intervals are provided in statistical learning. Okay, variance is provided in true Bayesian learning. Okay, they wind up being practically of similar uses. Okay, the big difference is actually confidence interval is not a probability, because you cannot make a statement about so its confidence interval is not a probability statement about the hypothesis, because hypothesis is a true God. It knows what it is, and you can't assume that it's randomly changing. The interval itself is your probability estimate. So there's an interesting technical point to be made that a confidence interval essentially is a probabilistic interval which just happens to capture the true hypothesis.
Okay, but we can do it in this way. For example, start with like a chi-square test. I mean, then improve our hypothesis or our belief by Bayesian learning. I mean, for example, say...
No, but I mean, that basically, then at some point of time, you're trying to allow hypothesis to be a random variable. That's a big difference, statistical... There is a good reason. Statistical learning was done where you are supposed to look for pattern in the data without any prior knowledge. And so it was right to not allow prior knowledge into the calculations. Okay. Whereas in an overall learning scenario, there is place for this. There is also place for small data learning, where if you don't use your background learning, you cannot actually do any useful learning at all.
But even they do, like for even like in the most basic goodness of fit test, they say, okay, let's try like normal distribution, and also let's try like maybe Poisson distribution.
I know, but the point is, again,
like
I think the point is similar to what I was making earlier, which is there are people who say that they're doing MLE, and they're doing MLE approach to topology learning, and then normally if you take them at their word, MLE approach to topology learning should just degenerate into complete topology. Okay, and so they will allow from the side some various scores, saying let's give some score, based on the complexity of the hypothesis. But that score makes no sense within that in MLE framework. It does have a meaning in the map framework. Similarly, if you are actually trying, let's try this versus try this versus try this, you are essentially assuming the hypothesis itself is sort of a random variable. You just don't want to call it that. By the way, I cannot convince, actually, it's like, this is a religious one. Okay, and if you are interested in it, by the way, you could look up on the videolectures.net Michael Jordan, who is actually a statistician and a machine learning guy, and I don't know how he sleeps in the night, but he has a lecture called "Are you a Bayesian or a Frequentist?" You should look at that, and that's a much more technical expose of the differing philosophies. But as far as this class is concerned, it's worth understanding at least these differences. Okay. Okay. Now, I guess the last thing I get to do is, should I also, which side should we go? I've been saying that machine learning guys fall on this side, statistics fall on this side. The real question is it reasonable for machine learning guys to fall on this side? Okay? And the problem normally is, what happens, should you distrust priors? If you are an AI person, should you distrust priors? And the answer to that is, eventually, data should be able to override your prior beliefs. But if you have no prior beliefs whatsoever, you will need a large amount of data to come to any reasonable decision. Okay? So, from an AI perspective, you really cannot say I would distrust priors. You have to allow priors over the hypothesis, because that's a way you talk about your background knowledge. All that I have known about this world has told me that when I get data for psychology experiments, they're always straight lines in the background. So then I just look for a straight line. In fact, there's a beautiful, you know, I might actually send it to you, a pseudoscience article about how to find straight lines hidden in the data. And then, for example, they'll say, you know, how to find a straight line in the sine wave. You know, you just assume that all the peaks are all noise, and then you draw a line through the midpoints, and that's a straight line. Okay, so if you're looking for one, you will find it. And the interesting thing is the background knowledge has given you those priors. Okay, if your prior is wrong, you will quickly come to a decision with even small data and might be wrong. But what else will you do if you only have small data? Okay. The thing, of course, is there is also evidence, at least people are trying to show that there is evidence that human brain actually uses priors. Different kinds of priors for different kinds of situations. Okay. So for example, for two different kinds of questions, I think, I cannot read this here. So one question is about, you know, amount of money that the richest versus the next richest person might have. The other question is about a different human lifespan. And you're making predictions. Now when you're making predictions, if you, for example, richness, if you assume that the wealth is distributed in a normal curve, then you would come up with very different answers than if you assume that the wealth is distributed in a power law curve. And the there's an interesting article that, you know, that is being said here, you can look it up. The kind of judgments humans seem to make can be explained in terms of they using a power law prior here versus a Gaussian prior here. That means they seem to know that for certain cases this is the prior, for certain cases this is the prior. Now, you know, a symbolic guys among us would say, well, this is the background knowledge. You know that wealth in the world is distributed in such a way, according to the Pareto's law, where rich get richer, and with tax cuts even more. But Gaussian prior, on the other hand, is for many other things where, for example, independently distributed, many independent variables, when they are summed to make the variable of interest, they tend to have, because of the, you know, central limit theorem, they tend to have a Gaussian distribution. Okay, so that's your background knowledge that you are bringing to bear. Okay, so I'll stop here. Next class, we will talk about essentially dimensions of statistical learning and how to do, and then more importantly, our agenda for that, for the rest of the semester would be, we'll focus on density estimation. We will assume first that we look at Bayes networks as the representation for the density to be learned. And if we have extra time, we will look at Markov networks. And then we'll focus on MLE as the first approach we'll use. And if we have time, we'll explain how to do Bayesian learning. Okay, while we are doing MLE, you know, you should remember that we are doing this because of intellectual laziness. And it will work well for large data kits. And then similarly, one other pass we will look at later on is, we will assume in the beginning that all the attributes are given up front. There are no hidden attributes. Whereas if there are hidden attributes, then it becomes a harder problem. So partial observability always makes life hard. Okay, and when there are these hidden attributes, one of the interesting questions is, you can just make as many of the hidden attributes as you want. Nobody tells you what attribute is hidden. Okay, so the question then is, what attributes are you going to assume exist? And normally the reason for that, if you remember your Bayes network discussions, when you put hidden nodes in a Bayes network, then the number of parameters reduces. If I have m nodes here and n nodes here and all m are affecting all n here, then I would need huge number of m times n number of, you know, conditional probabilities. Okay, now 2 power m times n number of conditional probabilities. Okay, whereas if I put one node in the middle such that all of those guys are affecting that node and that node is then affecting these nodes, then you reduce the number of conditional probabilities exponentially. So just by assuming structure, you reduce the number of things you have to learn. Okay, and we'll see how to use, but the problem of course is when there's a hidden variable, learning becomes harder because maximum likelihood estimation is hard to do because you don't actually know all the values for the data, all the attributes for the data. So this is what we'll be doing for the rest of the semester.